The determinant of a matrix A is a scalar number that's useful when computing the inverse of the matrix. This is another way to write it. Or we can put straight lines around the actual matrix. If the determinant is 0, then the matrix is not invertible. For a 2 by 2 matrix with components A, B, C, and D, the determinant will be A times D minus B times C. Calculating the determinant of larger matrices involves a more complex and recursive formula. To compute the inverse of a 2 by 2 matrix, we swap the components A and D, and we leave the components B and C in place, but we make them negative. Then we scale each of the matrix elements by 1 over the determinant. In other words, by 1 over AD minus BC. Notice that we swapped A and D, and likewise A and D are grouped in the determinant. Notice also that we made B and C negative, and likewise B and C are grouped in the determinant and negative. We can also understand determinants geometrically. First, consider that a linear transformation can be thought of as something that takes some area or volume from the domain and transforms it into another area or volume in the codomain. For example, this matrix scales area by 2 vertically and 2 horizontally. The determinant is the scaling factor of the area. In our case, because 1 unit of area is scaled to 4 units of area, the determinant is 4. Now consider this matrix, which scales 1 unit of area to 0 units of area, because it smushes the area to a line that has height 0. Because we've reduced the area from 1 to 0, the scaling factor, i.e. the determinant, is 0. This tells us that the matrix is not invertible because we've lost dimensionality. If the domain were in 3 dimensions, then any transformation that maps a unit volume to a part of a plane or line or to just the origin would likewise not be invertible.